So the problem presented is a classic example from the topic of bending stress in beams. So for this particular problem, we're going to dive into looking at the shear force diagrams and bending moment diagram. The shaft is supported by smooth journal bearings at A and B that only exert vertical reactions on the shaft. Determine its smallest diameter, D, if the allowable stress allowable is equal to 180 megapascals. The free body diagram shows the shaft supported by smooth journal bearings at A and B, which provide only vertical reactions. The UDL of 12 kilonewtons per meters extends from A to B 3 meters and continues for another 1.5 meters beyond B. So to simplify calculations, replace the UDLs with their equivalent point loads. The first UDL from A to B is 3 meters, which contributes a force of 36 kilonewtons, acting at its centroid 1.5 meters from A. The second UDL from B onwards contributes a force of 9 kilonewtons, acting at 0.5 meters from B. The reactions at A and B are found using static equilibrium, so the summation of forces in the y direction and the summation of moments at point A. After solving the reactions at A and B, we are given that AY is equal to 16.5 kilonewtons and BY is 28.5 kilonewtons. So at A, when x is equal to 0, the reaction force of AY is equal to 16.5 kilonewtons causes an upward jump in the shear force. Next, from A to B, the UDL gradually decreases the shear force. So there's a linear decrease in the shear force. The rate of decrease is equal to W, which is equal to negative 12 kilonewtons per meters. Over the 3 meters, the change in shear force is equal to negative 12 times 3, which is negative 36 kilonewtons. And at x is equal to 3, so just before B, the shear force is equal to negative 19.5 kilonewtons. So it's linearly decreasing shear from 16.5 kilonewtons to 19.5 kilonewtons between A and B due to the UDL. And this shows a straight diagonal line sloping down in the SFD. So next we have segment BC, so 3 meters to 4.5 meters. This segment has a triangularly distributed load, going from 12 kilonewtons per meter at B down to 0 kilonewtons per meter at the free end. So let's analyze this carefully. At B, the shear force is equal to 9 kilonewtons. This is because support B jumps the shear up by 28.5 kilonewtons. So the shear force changed. So the triangular load area is equal to 9 kilonewtons. Since this is downward, the change in the shear force is equal to negative 9 kilonewtons. So at the free end, the shear force change is equal to 0 kilonewtons. So next we'll draw out the bending moment diagram. To get the moment at each section, you integrate the shear force geometrically, which means finding the area under the shear force diagram. So the bending moment at each point is equal to the area under the shear force diagram up to that point. So shear force changes linearly due to the UDL, and the moment changes parabolically, so second degree curve. So first, when we're at point A, so when x is equal to 0, the bending moment is 0. Next, the bending moment between A and B is found by either integrating shear or finding the area under the shear force diagram. So max moment occurs where shear is equal to 0. From the shear force diagram, shear becomes 0 at approximately x is equal to 1.375 meters from A. So using the area under the shear force diagram, area is equal to 11.34 kilonewton meters. So this is the maximum moment as shown on the moment diagram. Next, the moment at B, so when x is equal to 3 meters. Using the area under the shear diagram from A to B, we have the area is equal to negative 4.5 kilonewtons. So the moment shape is a parabolic curve due to the linear shear force. Next, looking at segment BC from 3 meters to 4.5 meters. So shear force drops parabolically, so bending moment changes as a third degree cubic curve. We'll just get the moment at the free end, so when x is equal to 4.5 meters. Using the area under shear diagram between B and C, the area is equal to 0. So lastly, finding the diameter D. So using the flexure formula, stress max is equal to moment max times C divided by the moment of inertia. We have stress max is equal to 180 megapascals. The moment max is equal to 11.34 kilonewton meters. C is equal to diameter divided by 2, and the moment of inertia is equal to pi divided by 4 times diameter to the power of 4 divided by 16. Rearranging for D, we get the diameter is equal to 86.3 millimeters. In summary, the minimum recommended diameter of the shaft is 90 millimeters to ensure the bending stress does not exceed 180 megapascals.